You are tuned to Iri-e-learning, and I am your host, Teacher. For this state of matter lesson, we will examine the heating curve. Check the description box for links to the lessons for this unit. By the end of this lesson, we should be able to define the term heating curve and interpret the stages of a typical heating curve. We will now examine the principle of the heating curve. In the video just viewed, we observed that there was an ongoing heat supply, and the solid, which was ice, solid water, melts and changes into liquid water, and liquid water boils and evaporates into a gas, which we call steam or water vapor. So what exactly is the heating curve? A heating curve is a graphical representation of the transition between the states of matter when heat is added or supplied. When we say transition, we refer specifically to the change from the solid to the liquid to the gas when heat energy is supplied. We will dive right into the interpretation of a heating curve. Note, when constructing a heating curve, we typically start with the heating of a pure solid sample. That is, it contains no impurities, and the heat energy is continually applied to show the transition from one state of matter to the next. That is, from the solid to the liquid to the gas. Now, starting with a pure solid sample will ensure that the melting and boiling points remain constant during the transitions from one state to another. Otherwise, and let us have this for general knowledge, if we were to use an impure solid, the impure solid would melt at a temperature range that is lower than the melting point of the pure solid. And as a result, we'll end up with an impure liquid, which would have a higher boiling point than that of the pure liquid. Like any typical graph, the heating curve consists of two axes. We have our vertical axis, which is called the y-axis, and the horizontal axis, which is called the x-axis. We have placed our temperature scale on our y-axis, and temperature is usually assigned units of degrees Celsius or degrees Fahrenheit. And of course, the unit used depends on the country in which you live. That is, whether your country is using the metric or the imperial system. Now, if your country uses metric system, then you're more than likely to be using degrees Celsius for your unit of temperature. Now, on the horizontal scale, we have placed time, and time is usually given units of either seconds or minutes, and the units used would depend on how quickly or how slowly the solid melts. Both axes meet at a point called the origin, which usually has a zero value for both scales, that is, the temperature scale and the time scale, unless one axis is broken. However, we will not consider the case of a broken axis in this lesson, as it will be a topic for a future lesson. The first section of the heating curve is a slope or incline as represented by the red line that appeared on the graph. Now, you may have noticed that this graph did not begin at the origin or zero as would be expected with ice. And you can see where our graph actually started along the temperature scale, where we have our blue flashing circle. Now, for such a case, it would mean that this solid was not ice, but it may have been some other solid that was kept at room temperature. Therefore, the start temperature of that solid would be some value close to that of room temperature at the time of the experiment. Also, at that starting point on the graph, we know that the particles of the pure solid sample, they are closely packed, they have low energy, and they vibrate in a fixed position. However, as the solid heats up, the temperature of the solid increases with time, hence that slope, and the particles absorb heat energy, and as the particles absorb heat energy, they gain kinetic energy, and then the particles will vibrate vigorously. That is, the particles would vibrate much faster than they would at room temperature. Now, in terms of energy and particle arrangement, just remember at this point, the solid particles, even though they're being heated up, they are still in their fixed position in the regular arrangement, but they are vibrating vigorously. Now, the increased vibrations of the solid particles continue until some of the interparticle forces begin to break, at which point melting begins. And this initiates or starts the second stage of the heating curve, which is represented by the green horizontal line. And the horizontal line is also called a plateau. Now, the horizontal line indicates that the temperature is constant. That is, it doesn't change over time. And during this period, a change of state of matter occurs. Now, this first change of state would involve the transition from the solid to the liquid state as the heat is applied. And of course, this process is called melting. During melting, only some interparticle forces break, and as a result, what we have are clusters of particles moving away from each other, and there'll always be a mixture of solid and liquid once melting is happening, and the temperature remains unchanged during that period of time. Now, it's important to note that the melting temperature remains unchanged because the heat energy supplied is used to break the interparticle forces only, and it's not used to increase the kinetic energy or the energy of motion of the particles. So the energy used to break the interparticle forces is known as latent heat or hidden heat because it is not observed as an increase in temperature. Eventually, all the solid changes into liquid, at which point melting stops. The constant temperature at which melting occurs is called the melting point. We obtain the value of the melting point by extending the horizontal line to meet the temperature axis or the y-axis as shown by our green dotted line. And the point at which the line touches the temperature scale gives the value of the melting point of that pure solid. So we know that when heat energy is used to heat a solid, some of the interparticle forces break, causing clusters of particles to separate from each other, changing the solid into the liquid state. Once melting ends, the graph transitions into the third stage, which is also represented by a slope, as shown by the red line that just appeared on the graph. Now, the slope indicates that as the pure liquid is heated, the temperature increases with an increase in time. So at this point, the clusters of liquid particles absorb heat energy, they gain kinetic energy, that is the energy of motion, and as a result, they begin to move faster. Eventually, the liquid particles gain enough energy to overcome or break all remaining interparticle forces, which starts the fourth stage. And the fourth stage involves boiling and evaporation. During boiling, the energy supplied to the particles of the liquid is used to break all remaining interparticle forces. Individual particles therefore gain more energy and move further apart and escape the liquid, changing into the gas state. And this occurs at a constant or a fixed temperature at which the liquid boils, which is called the boiling point. Now, the value of the boiling point is obtained by extending the horizontal line to meet the temperature axis as illustrated by our green dotted line. And the point where the line touches the temperature scale gives the value of the boiling point. Note, when the particles of the liquid gain energy to break all interparticle forces, the individual particles move faster and far away from each other, entering into the gas state, and that process is called evaporation. As we saw earlier in the video, evaporation actually begins even before boiling starts, because the particles at the surface of the liquid can overcome interparticle forces and escape into the gas state. Also, for more details on the difference between evaporation and boiling, you can review the lesson on changing states of matter. Check the description box for a link to that lesson. That brings us to the final stage of the heating curve as represented by the slope shown by the red line that just appeared on the graph. The slope indicates that as heat is applied, the temperature of the gas increases with an increase in time. As a result, the individual gas particles gain more kinetic energy, that is the energy of motion, due to the weakened interparticle forces, causing them to move rapidly and further away from each other. As a matter of fact, they become widespread, occupying all the space available to them. Now that we have completed the analysis of the heating curve, you may have noticed two repeating trends. We have the slopes, which are our red lines, and our horizontal lines, which are in green. Now, the slopes indicate the existence of a specific state of matter, solid, liquid, gas, for which the temperature of each one is increasing with time as heat is applied. Now, the horizontal lines, on the other hand, show the process that changes from one state of matter to another, and that involves melting when you change from the solid to the liquid, and boiling and evaporation when the liquid changed to the gas. Let us review the lesson summary. A heating curve is a graphical representation that shows temperature changes for changes in the states of matter from solid to liquid to gas when supplied with heat energy. Temperature is always placed on the y-axis and time on the x-axis for the heating curve. Particles within any state of matter gain more kinetic energy when supplied with heat energy. An increase in the kinetic energy of particles causes an increase in the temperature for the given state of matter, that is, for the state of matter of the substance being heated. Latent heat, also known as hidden heat, is the energy used to break the interparticle forces. Latent heat is never observed as an increase in temperature on a thermometer. Melting and evaporation occur at fixed temperatures for pure substances. Those are solids and liquids, respectively. It's quiz time, and you have 5 seconds to answer each question after it has been read aloud. Question 1. Which statement best describes latent heat? A. Heat that increases the kinetic energy of the particles. B. Energy that is observed as an increase in temperature. C. Heat that increases the kinetic energy of solid particles. D. Energy that is used to break interparticle forces. The answer is D. Energy that is used to break interparticle forces. Question 2. Which statement is true about a pure solid? A. A pure solid does not contain any impurities. B. A pure solid is a mixture. C. A pure solid contains impurities. D. None of the above. And the answer is A. A pure solid does not contain any impurities. Question 3. Identify the statement that is true about melting a pure solid. A pure solid, A, does not melt at a fixed temperature. B, melts at a lower temperature than the impure solid. C, melts at a fixed temperature. D, none of the above. And the answer is C. A pure solid melts at a fixed temperature, or sometimes we would say it melts at a constant temperature. Question 4. What quantity is placed on the y-axis of a heating curve? A. The strength of the interparticle force. B. Time. C. Temperature. D. The number of broken interparticle forces. And the answer, of course, is C. We place a temperature scale on our y-axis. Question 5. Identify the statements that are true about melting a pure solid sample. Number 1, the melting temperature remains constant. Number 2, melting involves a change from a solid to a liquid when heat is removed. 3, latent heat breaks the interparticle forces. 4, melting ends when there is a mixture of a solid and a liquid. And our answer options are A, 1, 3, and 4, B, 1 and 3, C, 1, 2, and 3, and D, 1 and 2. The answer is B, 1 and 3. So let's see why statements 2 and 4 are incorrect. Now, statement 2 is incorrect because changing from a solid to a liquid requires the supply of heat energy and not the removal. And 4 is incorrect because melting ends when all the solid changes to a liquid. However, during the process of melting, there would be a mixture of the solid and the liquid. We have reached the end of our lesson. If you found this video helpful, remember to like, share, and subscribe. When you subscribe, you'll receive notifications as new videos are uploaded. So until next time, I am Teacher with Iri-e-learning.